Imagine you're in a room with absolutely no light. It's completely dark. How would you find your way around? You might slowly put your hands out, feeling for walls, furniture, and obstacles. Yet, some animals do this every single day, or rather, every single night. A bat can fly through a dense forest at high speed in total darkness, catching tiny insects without ever crashing. How does it do it? How can it see when there is no light? The answer is a kind of natural superpower, one that uses sound instead of light. And what's even more amazing is that we humans have learned from these animals, creating technology that lets us see in the darkest places on Earth. Have you ever shouted into a large empty hall or across a wide canyon? A moment later, you might hear a faint copy of your own voice shouting back. That's an echo. An echo happens because sound doesn't just travel outwards and disappear. When sound waves hit a solid object, like a distant cliff face or the wall of a building, they bounce off and travel back to your ears. This simple idea is the key to understanding how animals navigate in the dark. They don't just hear echoes by accident, they create them on purpose. This amazing ability is called echolocation. Echo, for the sound that bounces back, and location, for finding the position of an object. Essentially, these animals are using sound to paint a picture of the world around them. But how does that even work? This presents a huge challenge. It's one thing to hear an echo, but it's another thing entirely to use it to build a detailed mental map. A simple echo just tells you something is out there. It doesn't tell you what it is, where it is, or how far away it is. To solve this, nature came up with an incredibly clever system. It's not just about making a sound and waiting for it to return. It's about listening to the tiny details hidden within the echo. The real problem wasn't just about creating sound, but about decoding the information that the returning sound waves carry. To understand this, we first need to understand what sound is. When you speak or clap your hands, you are creating vibrations in the air. These vibrations travel outwards as invisible waves, similar to the ripples that spread across a pond when you drop a stone in it. These are sound waves. When these waves reach our eardrums vibrate, and our brain interprets these vibrations as sound. Echolocation works by sending out these sound waves and then carefully analyzing the waves that bounce back. Think of it like throwing a ball in a dark room. You can't see the wall, but if you listen, you can hear when the ball hits it. If you time how long it takes for the sound of the bounce to get back to you, you can figure out how far away the wall is. Animals that use echolocation are doing this thousands of times per second, but with sound waves instead of a ball. These clicks travel out into the environment. When they hit an object, like a moth, an echo bounces back to the bat's very sensitive ears. The bat's brain is like a super fast computer. It measures the time delay between when it made the click and when it heard the echo. A short delay means the object is very close. A longer delay means the object is farther away. This is how the bat calculates distance. But what about direction? A bat has two ears, just like us. If an echo arrives at the left ear a fraction of a second before the right ear, the bat knows the object is to its left. The bat can also tell how big an object is. A large object, like a tree, creates a loud, strong echo. A small object, like an insect, creates a faint, weak echo. Even more incredibly, the texture of the object changes the quality of the echo. A smooth leaf sounds different from the fluttering wings of a moth. By putting all this information together, distance, direction, size, and texture, the bat builds a rich, 3D sound map of its surroundings in real time. This incredible skill isn't just for animals that fly. It's also used by animals that live in the deep ocean, like dolphins and whales. Water is a fantastic medium for sound. Sound waves travel over 4 times faster in water than they do in air, and they can go much, much farther. These clicks bounce off fish, rocks on the seabed, and other dolphins. The returning echoes are picked up by the dolphin's lower jaw, which transmits the vibrations to its inner ear. Just like a bat, a dolphin uses the time delay of the echoes to judge distance and direction with pinpoint accuracy. But dolphins can do something even more amazing. Because the sound waves can travel through soft materials, a dolphin's echolocation can see inside things. It can tell the difference between a fish and a rock of the same size, because it can detect the fish's swim bladder, an air-filled sac inside its body. For dolphins and whales, echolocation is like having a pair of X-ray goggles, allowing them to navigate and hunt in water that is often dark or murky. For centuries, humans knew this was happening in nature. Scientists studied bats and dolphins, amazed by their abilities. Then, they asked a powerful question: can we do that too? The answer was yes. We created our own version of echolocation, and we called it sonar. SONAR is an acronym that stands for Sound Navigation and Ranging. It works on the exact same principles as the echolocation used by animals. A submarine, for example, can't use windows to see where it's going in the deep, dark ocean. So it sends out a pulse of sound called a ping. This ping travels through the water, bounces off any object in its path, like another submarine, an underwater mountain, or the ocean floor, and returns to the submarine. There is also passive sonar, which is just listening. Submarines can turn off their own pings and simply listen for the sounds made by other ships and submarines to find them without giving away their own position. Ships on the surface use sonar for a different reason: to map the ocean floor. By sending pings straight down and measuring the echoes, they can create detailed maps of underwater mountains, canyons, and shipwrecks. Fishermen use a smaller version, called a fish finder, to locate schools of fish beneath their boats. It's the same technology, just on a different scale. From medicine, where ultrasound uses sound waves to create images of inside the human body, to engineering, we have found countless ways to use the power of echoes. So what is the big insight here? It's the realization that seeing isn't just about light. Seeing is about gathering information from the world around you, whether it's light waves hitting your eyes, or sound waves hitting a bat's ears, or a submarine's detector. The fundamental principle is the same. Nature is the ultimate engineer. It solved the problem of navigating without light millions of years ago. By observing and understanding the natural world, we can find inspiration for some of our most powerful technologies. Echolocation and sonar show us that a simple idea, like a sound bouncing off a wall, can be turned into a sophisticated system for exploring worlds we could never see on our own. A bat chasing a moth, a dolphin hunting for fish, and a submarine exploring the ocean depths are all connected by this one brilliant idea. They all use invisible waves of sound to illuminate the darkness, turning echoes into sight. The world is full of invisible information, and with the right tools, we can learn to see anything.